Both the standard enthalpy and the standard entropy of a reaction depend on temperature. And we'll look at the temperature dependence here. For a general chemical reaction from A to B at room temperature, if both A and B are in the standard state, we have this standard enthalpy of reaction at room temperature equals the standard enthalpy of B at room temperature minus the standard enthalpy of A at room temperature. And if we use pure elements as the zero reference, this can be replaced with the enthalpy of formation of B. This can be replaced with the enthalpy of formation of A. And we have a similar equation for entropy. And usually we can look up these two values, the standard enthalpy and entropy of the reaction at room temperature, from the CRC handbook or the NIST website. So what if we need the values of the standard enthalpy of the reaction and the standard entropy of the reaction at a different temperature? Well, at a different temperature, we can still manage to compute this enthalpy of reaction and entropy of reaction in the standard state by breaking this reaction into 3 steps. In the first step, we change the temperature of A from T to room temperature. In the second step, we allow the reaction to proceed at room temperature. In the third step, we change the temperature of B from room temperature to the target temperature T. Therefore, the enthalpy change of the reaction includes 3 terms. Over here, that's the enthalpy change of A from temperature T to room temperature. This is available to us. This is just the enthalpy of reaction at room temperature. The third term is the enthalpy change of B when temperature changes from room temperature to T. We can combine these 2 terms here. The reason is we can swap the lower limit and upper limit by adding 1 negative sign in front. Therefore, we have this integral here. And given constant pressure, the H is simply Cp dt, and we can take out the common factor dt. Therefore, inside this square bracket, we have Cpm of B minus Cpm of A. We put a molar here is because the enthalpy of reaction is typically in joule per mole or kilojoule per mole, and we use this to describe the enthalpy change of the reaction per mole reaction. That's why we need the molar here. And again, this is in joule per mole or kilojoule per mole. This should also be in joule per mole and kilojoule per mole. And then we use delta CPM to denote the change of the CPM of the reaction. So in general, it's just the CPM of the products minus the CPM of all reactants. So again, in sum, the standard enthalpy of the reaction at temperature T equals the standard enthalpy of reaction at room temperature plus a correction. The correction is the integral of delta CPM dt from room temperature to the target temperature. For entropy change, we use similar analysis. The entropy change of the reaction equals, again, the standard entropy change of the reaction at room temperature plus a correction here from room temperature to the target temperature T. Inside this is the molar entropy of the products minus the molar entropy of the reactants. And we know the definition of ds is dq reversible over T, assuming we are using a reversible process, and we can convert this ds to be dq over T. So we have dq of B minus dq of A. And because the process is isobaric, we convert dq to Cp dt. Therefore, we have Cp of B minus Cpm of A times dt over T. I'm sorry about the mistake here. And this Cpm of B minus Cpm of A is simply the change of the Cpm in the reaction. And again, if you look at these 2 equations, this entropy change of the reaction at temperature T is the standard entropy change of the reaction at room temperature plus a correction. This is just the integral of delta CPm dt over T from room temperature to the target temperature. And for enthalpy, we have a similar correction. The only difference is this. In here, we integrate delta CPm for the enthalpy correction. Over here, we integrate delta CPm over T for the entropy correction. And in general, we do not have to have just one reactant and one product. We can have any number of reactants and any number of products as long as you understand this delta CPm as the sum of the CPm of all products minus the sum of the CPm of all reactants. And also, we do not have to compare target temperature with room temperature. We can just simply do this T1 from T1 to T2. We can compute the standard enthalpy of reaction at temperature 2 given the standard enthalpy of the reaction at temperature 1. So it can be more general. And also, it does not even have to be the standard state. As long as the pressure is constant, we can always say dH equals Cp dt. We can always say this ds equals dq over T in the isobaric process. So really, the derivation and analysis can be applied to just any two different temperatures. It can be applied to a different pressure as long as the pressure is held constant. Also, it can be applied to a general chemical equation that involves multiple reactants and multiple products.